This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. This is section 5.33, logarithmic functions and graphs. We're going to stick around with logs for just a little bit longer on this third day, and today we're just going to be trying to graph them. So here's what this looks like. If you have the graph of y equals log base 5 to the x, that's the same thing as 5. Remember, this is the base, 5 is the base. Y would therefore be the exponent, and x would be the power. And if you wanted to, maybe it's easier to choose the y values and then calculate x. Because here you can see, choose the y values. You're able to plug all those in here for y and calculate what x would have to be. It's a lot easier to do it that way. So you can choose, say, for example, -2, -1, 0, 1, 2, and then put them in here in the exponents. You're choosing the exponents first and then calculating the powers. And remember, the powers are over here because the powers are the input to the log function. And when you graph it, it looks like this. Here is the x-intercept, 1, 0, right here. And here's some of the other values, -0, 0.2, -1. And that's that. Oh, you might ask, Bergman, how do we get these decimals? And I'll tell you, -5 to the -1. Remember, negative exponents indicate fractions. So 5 to the -1 would be 1 over 5. It's the same thing. 1 over 5 is the same thing as 0.2. 1 over 25 would be the same thing as 0.04. Anyway, there it is. Another way to think about it would be to say y equals log base 5 of x. And so you could graph the inverse and then reflect. The inverse would be changing these around like this and reflect. I don't much like that, but I wanted to show it to you anyway. You would have these x values, the same x values and the same y values, and then make sure you reflect them. So change these to x values and change these to y values and graph. Anyway, any way you do it, you get this graph. And that's what it looks like. It's a reflection of the exponential graph. Let's graph each as a transformation of the parent function. So if the parent function is y equals natural log of x, and the natural log, meaning base of e, says give the domain and the vertical asymptotes. Okay, well, here's the parent function. Remember, 0 is undefined. 1 is going to create 0, because if the power is 1, then it should have an exponent of 0. If the power is 2, then it should have an exponent of 0.69. If the power is e, then it should have an exponent of 1. It's the natural log. So the graph of y equals natural log of x is going to have a domain of 0 to infinity and a vertical asymptote at x equals 0. We can kind of see that here. The natural log of x is similar to the log 5 of x. It has this domain it cannot equal 0, but it has a domain of all positive numbers from 0 to infinity, and it has a vertical asymptote at x equals 0. Now, what about this? F of x is equal to natural log of x plus 3. Well, that should be very similar to the graph of the parent, except that it's going to have a shift of -3, a horizontal shift of -3 units. So you can actually even just use the same table if you wanted to. Like if you had this table, I'm just going to shift these over: -3, -2, -1, and then 2.72 minus 3 is -0.8. And you can see that this is going to be here undefined, 0, 0.68, and 1. You can plug those in, but it's going to be a shift. And the shift means that since there's a horizontal shift of -3, it's going to have a domain that's further over. This domain goes to -3, and there's a vertical asymptote at x equals -3. All because of this x plus 3 right here. Here, f of x is equal to 3 minus 1/2 of natural log of x. We've got a c value of -1/2 and a d value of 3. That means it's going to be a vertical dilation by a factor of -2. I mean, here's the original. It gets flipped over because the negative 1/2 is negative, and it's going to shrink a little bit because it's negative 1/2. Then, of course, we're going to have a vertical shift of 3 from this 3 right here. The d value is 3. So 0, 1, 2, 3, if you plug those in here, you're going to get something that's undefined at 0 and these points, and you can plot them, and there it is. This has a vertical, it has a domain of 0 to infinity, just like the original parent, and a vertical asymptote is x equals 0, just like the original parent function. What about the absolute value of the natural log of x minus 1? Well, here's the parent, and if you add, if you shift it to the right 1 here, then it'll look like this. You can see that this green graph is shifted to the right, especially here for these 2 points. Let me see again. So you can see that this original blue point gets shifted to the right 1 unit. This blue point gets shifted to the right 1 unit. This blue point gets shifted to the right 1 unit. And then we're going to take the absolute value of all that. So any negative values that used to be down here get reflected up so that they're positive. That's what the absolute value does. It's going to have a vertical asymptote at not x equals 0, but as x equals 1, because the whole graph gets shifted over 1 unit. Vertical asymptote at x equals 1, and the range is therefore, the domain is also going to be 1 to infinity. Now might be a good time for me to tell you about the periodic table element for the day. It's iron, and iron helps us play. Example 12, walking speed. In a study by psychologists Bornstein and Bornstein, it was found that the average walking speed, W, in feet per second of a person living in a city population, P, in thousands, is given by this function. And it's actually kind of interesting. I've experienced this. When you live in small towns, people walk slow. When you live in really big cities, people walk fast. It's not like it's a huge difference, but the more people there are in a city, the faster they're going to walk. And they found this relationship. Here, so the population of Savannah, Georgia is 136,286. Find the average walking speed of people living in Savannah. So you take this value, P, it's a P value for the population, you plug it into the function and see what you get. You get 136.286. This is actually measured in thousands of people. So here it is. You put it in for x, or for p, and then you take the natural log of it, you multiply it by 0.37, and you add 0.05. And you get 1.87 feet per second. That's how fast they're walking. You can even find it on this graph right here. I mean, part C says to graph it, but I might as well point out that part A's answer is right here on the graph. 1.868 feet per second. The next question is population of Philadelphia. Go Philly. 1,526,000. Wow, we have a lot more people in the city now than we used to. So this here is 1,526. You remember this is measured in thousands. P is measured in thousands here, so we have to convert this to how many thousands. That's what that is. You put it into the function and you get out 2.76, and here it is on the graph. This is the population, and this is the walking speed, approximately. You can graph it like this, and then a sociologist computes the average walking speed in a city to be approximately 2 feet per second. Use this information to estimate the population of the city. So here, the table would look like this. 0 is undefined, because if you have a population of 0, you can't figure out how fast they walk. But if you have a population of 136, it's a speed of 1.8. If this is the input, the population, and this is W, the output, the walking speed. And so what I want you to do is to look at this graph. The number appears in 2 different places, but I want you to figure out what population is going to produce a walking speed of 2. And you can look at it on the graph or even on the table. And then after that, I want you to begin assignment 5C3, copy the problem list, and do the first problem, and I will see you in class.